Hello. Okay. Welcome to today's colloquium. It is our pleasure to welcome Professor Supratik Pal of Indian Statistical Institute, Kolkata at IMSC for the institute colloquium. Professor Pal works in different areas of cosmology and gravitation. He got his PhD from Jadavpur University, Kolkata. After that, he was postdoctoral fellow at IUCAA, Pune, and Bonn, Germany. He is a recipient of prestigious Alexander von Humboldt Fellowship of Germany twice. One is at University of Bonn and Max Planck Institute for Astrophysics, Garching. And he also received the Platinum Jubilee Fellowship from ISI Kolkata, and he also received the Young Physicist Award from Indian Physical Society. Apart from his research works, Professor Pal is well known for popularizing science with his public talks. I must mention his recent book in Bengali, Mahakasher Boitok Khanai, also translated as In the Meeting Room of the Cosmos, which was released last year. In cosmology, Professor Pal works on different areas, including dark energy, on which I have a paper with him as well, inflation 21 centimeter, CMB observation, etc., but not limited to only in these topics. He is a member of the Executive Council and Science Subcommittee of the Astrophysical Mega Project Square Kilometer Array, or SK India. And he is also a member of the Cosmic Microwave Background India Consortium, which is also known as CMB Bharat. So today we are really happy to have him, and he is going to talk about how many parameters for our universe. So I'll leave the stage to you, Professor Pal. Thank you.
Am I audible? Great. So first of all, let me thank Dheeraj for inviting me here and for giving a very nice introduction. And also thank you everybody who are present here, either in person. Overview on the cosmological models of our universe, particularly focusing on dark energy, keeping so. Of course, I'll be focusing mostly on the recent observations of late. And since I'll be giving a colloquium, I mean, most of the parts may be sounding obvious to the experts, and I beg your apology for that at the very beginning. So as the title of my talk suggests, I will be trying to explaining, or rather trying to find out how many parameters are required to explain the observations in our universe as a whole. And what I do is that before I start giving my lecture, I usually try to give the summary of my talk, so that if you get bored, we don't know as of now. Is to discuss the journey about finding out about the parameters of our universe. So that is what I'm going to discuss. Okay. So here are some random questions that I'll try to elaborate upon in the next 40-50 minutes or so. So how do you know about that, first of all? Why is that surprising at the very first place? And then who drives this acceleration? These three things will be mostly complemented by theory as well as experimental data, so to say. After that, these will be the main focus of my talk. What is our current understanding of the universe, where I will try to corroborate theoretical models with the experimental data sets. So these will be the main focus of my talk. Then I will try to elaborate on this, how conclusive is our understanding. Is our understanding really, really clear about the universe? Do we really know about how many parameters are required in order to explain the universe or not? And finally, I will try to give a very brief overview on this topic, which I am currently working on. In particular, can future missions help somehow in this regard or not? By future missions, I'll elaborate on what kind of missions I'll be talking about. Okay. So here is a brief history of my talk, rather brief history of the universe, so to say. This is a cartoon. This was the cover page of 1998 Science magazine, and it basically tells you, advocates for the accelerating universe, so to say. And it basically tells you that this accelerating universe, the invention of the detection of accelerating universe, this is a breakthrough of the year 1998. More than 20 years down the line, as it turned out, this is not only a breakthrough of the year 1998, this is still a breakthrough of modern cosmology, so to say. So, before going into details of all these things, let me try to explain, what I mean by accelerating universe. There are some, even before 1998, there has been some early signals through which the experimental cosmology as well as the theoretical cosmology basically passed. The very early stage of observational cosmology that basically came with the help of rather Edwin Hubble in 1929. During that time, what he was trying to do is that sitting on our Milky Way galaxy, he was trying to measure two different parameters of the nearby galaxies. One is the distance of the galaxy from us, other one is the velocity of the galaxy. And then what he did is that he drew a very simple plot. Along the x-axis, he drew the distance, along the y-axis, he drew the velocity, and each data point is a galaxy over there, so he just drew the data points over there. Then what he tried to do is to draw a mean curve through those data points, and to his utter surprise, what he found out is that this mean curve is nothing but a straight line. And from this mean curve, from the slope of this mean curve, using a very simple formula V equals h naught d, one can find out the rate of expansion of the universe, which is called the Hubble parameter. So this Hubble parameter, as it turned out, this is the coolest parameter, which is by definition is a constant, okay? And this constant, as it turned out, this constant plays a very important role in today's cosmology. So from here, the essential conclusion is that further the galaxy is, greater is its motion away from us. This is obvious from this plot. So essentially, galaxies are basically moving away from each other, and the entity that is responsible for this kind of movement is called our universe. So our universe as a whole is expanding. Because our universe as a whole is expanding, we see that the galaxies are basically moving away from each other. So this is the conclusion. Of course, the value of Hubble parameter that was measured by Hubble around that time was a very large one. As the time goes on, with the advent of new experiments, this value has been shifted to a great extent, but nevertheless, this is a very important detection so far as present observational cosmology is concerned, which basically tells you is that our universe is not static, it is basically expanding. So that's it. The second early signal came by the name of cosmic microwave background radiation. During the year 1963 to 65, these two guys, Penzias and Wilson, in the Bell Laboratory in USA, what they tried to do is to do something else, but just out of curiosity, they received some data and they tried to analyze the data. And that data basically tells you is that along x-axis they tried to plot the frequency, and along y-axis they tried to intensity of the wave that is basically they have been receiving. And once again, to their utter surprise, they found that this basically satisfies the black body spectrum. So essentially, what it tells you is that this cosmic microwave background, the earliest possible signal that is coming towards us, I will talk about the numbers and figures in details later on, but that basically tells you is that our universe is black body as a whole. Okay? So essentially, the temperature of our universe is same everywhere. They can give an estimate of the temperature as well. I will talk about that later on. So, as it turns out, this cosmic microwave background that turns out to be a gold mine of information. So lots of other experimental observations came dedicated to CMB like COBE, Planck, WMAP and Planck, and they basically tells you even though the temperature is same at the leading order, there are very tiny temperature fluctuation. How much tiny? This is 1 part in a million. But our experimental sophistications can help us in detecting these tiny temperature fluctuations, which goes by these color codes. The bluer basically means there is a temperature drop, and redder and yellower and redder basically means there is a temperature rise. So from these very tiny temperature fluctuations, I will tell you in a minute later on that from these temperature fluctuations, one can also say that our universe is expanding, although indirectly, by fitting some models. Third early signal came by the name of large scale structure. Once again, this follows from cosmic microwave background. This is a snapshot of our universe. This is actually the earliest possible snapshot of our universe, which is at a redshift of around 1100. From here, the large scale structures basically formed, and do you see these large scale structures in form of galaxies, clusters, and so on and so forth around us. So these basically tells you that the photons in the large scattering surface, photons remain as the background, and baryons, they basically start oscillating around the photon. That oscillation of the baryons, that goes by the name of baryonic acoustic oscillation, and Sloan Digital Sky Survey data. From there, there is a part which is called BOSS data, Baryonic Acoustic Oscillation Spectroscopic Survey data, that basically can give us a measure of the amount of total matter, dark matter plus baryonic matter that is required, which indirectly once again gives us a hint about the acceleration of the universe. I will come to these things slowly and slowly. Then the breakthrough came in 1998. I have already talked about the breakthrough. Three guys, Rees, Perlmutter, and Smith, they independently, they tried to measure a particular kind of supernovae called the type 1a supernovae. And these type 1a supernovae, collecting the data, once again they tried to draw some plot. This is rather a later plot which is called Union 2.1. At that time, the data set was not that rich, but they had around 48, 50 data points. But what they tried to do is that along x-axis they tried to plot the redshift, and along y-axis they tried to plot something which is called the distance modulus of the supernovae. And the data points that more or less look like this, as I already said, this is a more later data points which is much more rich. But essentially the flavor is something like that, which actually tells you, in order to explain this data, our universe has to accelerate along with the expansion. So as I told from Hubble data, you can say that our universe is expanding, but from supernova data you can say about the rate of expansion of the universe, and it basically tells you that the rate of expansion is basically accelerating. So essentially it tells you our universe is not only expanding, but also accelerating. Okay, so here is the summary. If I collect all these data sets together, supernovae, CMB, BAO, and etc., then all we can say is that these are typically the contour plots. Along x-axis there is this omega matter, along y-axis there is omega dark energy, so on and so forth. It basically tells you all these data points, they basically converge to some values, which taken together tells us that our universe is accelerating at present. Not only that, it basically tells you that this is a very recent phenomenon. This is a cartoon. This gives you a timeline of the universe. Universe started from Big Bang, and then there was this inflationary phase. After that, cosmic microwave background came, then dark ages came, then the first light started forming, galaxies, clusters, all of them started forming, and we are sitting here today looking back in time. So this is a cartoon, and it basically tells you is that our universe is not accelerating from the very beginning. At the very beginning, our universe accelerated, for sure, that is called inflation. After that, there are decelerating phases which go typically by the name of radiation dominated era, matter dominated era, so on and so forth. And very recently, when the redshift was around 0.56, that is the size of our universe is around 60% of the present size, universe once again started accelerating. So by acceleration, I am basically trying to mention this late acceleration of the universe. I am not talking about the inflation. Although I will connect all these things throughout the evolution history of the universe. Now, why is this surprising? Yes, fine, our universe is expanding, that is not too surprising. Our universe is accelerating, that should not be too surprising as well. So why we are so much bothered about the acceleration of the universe? Let me try to elaborate on this little bit. As we know, gravitational force is essentially attractive. There is nothing called negative mass, unlike electrodynamics. So gravitational force is essentially attractive, and the evolution of the universe that basically goes by these two equations, which are called Friedmann equations. I mean, because I'm pretty sure all of you know about this, but let me try to elaborate on this. This A is called the scale factor, which actually gives you a measure of the size of the universe with time. And this rho is the density of the universe, P is called the pressure of the material component, okay. So these two equations, I will try to focus on the second equation, which basically gives you the acceleration term in the right hand side. So A double dot is sitting there in the left hand side. So in order to give acceleration, the right hand side should be positive definite. Now as we know, rho and P as the density and pressure, which should be positive by virtue of this strong energy condition, rho plus 3p should be greater than or equal to 0. So the term within the parenthesis should be positive using our usual perception. 4 pi g by 3 is a constant for sure, but there is a negative term sitting over there. So, this negative term essentially tells us that our universe should decelerate no matter what kind of material component we put in the right hand side. But our observation basically tells you that the left hand side is accelerating. So, there is a sign mismatch between these two sides, and essentially our universe is accelerating essentially means the ordinary matter that satisfies the strong energy condition cannot supply this effective anti-gravity which is required for acceleration. So, essentially there is a mismatch, surprisingly mismatch between theory and observation. Theory, our usual theoretical perception basically tells you that our universe should decelerate, whereas all these experiments taken together, they basically tells us that our universe is accelerating. Okay, not only that, these experiments can give us a measure of the material candidate that is responsible for acceleration. This is the so-called cosmic pi. It basically tells you that within the cosmic budget of the universe, 5% at most should be baryonic, around 25% should be dark matter, and around 70%, a huge amount, should be attributed to the candidate which is responsible for the acceleration. Because our universe is, the material component, because the gravitational force is attractive, they basically try to tend all of them closer to each other. So, there must be a force which is more dominant than that one, which should pull them apart, and that force generically calls, force is a very vague term, I should not talk about that. A material candidate that is responsible for the acceleration of the universe should be constituting to 70% of the energy budget of the universe, and that generically goes by the name of dark energy. So, essentially it tells you is that there should be some candidate which somehow should violate the strong energy condition so as to explain the present acceleration of the universe, and the generic name attributed to that candidate is dark energy. But then, if it is not surprising enough, it is not fun. Why should we do science? Because there is something surprising, something fun. So, that is why we will do science. And because dark energy is essentially a surprising candidate, people tried to rather propose different dark energy candidates, all of them violating the strong energy condition, so as to explain the present acceleration of the universe. And here is a so-called rather incomplete list of dark energy models. Under each category, there are lots of different models. I just categorized them into some broader generic names. The simplest possible candidate is called cosmological constant, and this goes by the name of vanilla model. This is the vanilla model because that is the simplest possible candidate. I will try to explain that later on. This has only 6 parameters, and this is generically called lambda CDM model. Lambda stands for cosmological constant, and CDM stands for cold dark matter. So, in the simplest possible scenario, our universe is made up of 6 parameters, made up of this cosmological constant CDM along with some other parameters. I will talk about those parameters later on. But as it turned out, people tried to play around with other models. So, they tried to make life more interesting, and they tried to propose different scalar field models as well as modified gravity models. And all of this taken together has been summarized over here. So, there are different scalar field models where the scalar field energy density and pressure that can be written down in the form of Lagrangian, and depending on what kind of scalar field we consider, we can basically categorize them in different classes called quintessence, k-essence, tachyonic, phantom, so on and so forth. Now, the third category is even more interesting because we have this Einstein's equation from where this Friedmann equations came. People tried to say why instead of rather modifying the right hand side, modifying the matter sector, let us try to modify the gravity sector, let us try to modify the geometry side. And that generically goes by modified gravity. Once again, there is a plethora of models. Some of them are purely phenomenological, some of them rather come from a fundamental theory, low energy realization of the fundamental theory, starting from Lagrangian and so on and so forth. From there, one can write down this modified gravity theories. Once again, this is an incomplete list. Some of them are called Brans-Dicke theory, F over gravity, Brainwald's or DGP model, so on and so forth. So, at the end of the day, all I want to say is that our intention was to explain one simple candidate, dark energy. And we end up at a number of models, a plethora of models. Now, this is, of course, this is interesting, but this is not too fun, so to say. We are trying to explain one simple thing, and at the end of the day, we have arrived at so many models. Then at some point, cosmologists thought that let the model building practice go on, but let us try to introduce something more smart. And what can be that one? Let us try to parameterize the parameters. Instead of proposing individual models, let us try to parameterize dark energy parameters. Why? Because of the simple thing that data is not directly sensitive to models. Data is sensitive to models through parameters. So instead of proposing individual models, let us try to parameterize the dark energy parameters in such a way that one simple parametrization may in principle take into account several models. So if we constrain that parameterization using data, we can in turn map that constraints to the individual models. Our job will be much more simple. Okay. Now observationally, we can probe 2 or at most 3 parameters of dark energy. One is the simplest density parameter, omega dark energy, which can be probed by probing omega matter. This was a very early practice. At the very beginning, people tried to parameterize dark energy density parameter. Second one, and the most popular one, which I will concentrate upon, is the equation of state parameter of dark energy. As I said, there is density and pressure. So pressure by density will be the equation of state. So we'll try to parameterize the equation of state of dark energy. And the third one, which is rather less popular, but that is gaining more popularity of late, is called the sound speed of dark energy. This will come into play whenever we consider the perturbations of dark energy. I will talk about that later on. For this, sorry? Absolutely, absolutely.
Okay.
Absolutely, of course. Thank you very much for pointing that out. Okay. So for now, what I will try to do is that I will mostly try to concentrate on the second parameterization, that is the equation of state parameterizations. Once again, as we said, we started with the number of dark energy models, and as it turns out, one single parameterization is unable to reflect all of them. So instead of one single parameterization, people tried to propose at least couple of parameterizations, which will make our life little bit simpler than constraining individual models. As I said, there is no unique dark energy parameterization, so I will talk about the most popular dark energy parameterizations, and I will try to constrain the parameters of dark energy using data sets later on. So the most popular dark energy parameterization goes by the name of CPL parameterization, where the equation of state for dark energy can be written like this, where this W naught basically tells you the equation of state for dark energy today, and if there is any redshift dependence of dark energy, that equation of state that can be attributed to this parameter. So this is the simplest and most widely accepted parameterization, and essentially if you consider CPL parameterization, then your universe is 6 plus 2 parameter description. So for lambda CDM, once again let me try to remind you that for lambda CDM, because there is no such equation of state for dark energy, for lambda the equation of state is only -1, so there is no such parameter as such. This is a 6 parameter description. For CPL, we have a 6 plus 2 parameter description. More or less, I'll come to those points slowly and slowly. Thank you once again. I'll come to those points. And I'll talk about, just like CPL, I'll talk about the other parameters as well. The second parameter looks a little bit more complicated, and deliberately putting these parameterization, I'll tell you why in a minute. Second parameterization is a SS parameterization. Unlike CPL, this is a 6 plus 1 parameter description. So basically, we need one less parameter compared to CPL, which is good from statistical point of view. But this looks very, very funny. All this includes is that W naught is the present equation of state of dark energy, and everything else, all the redshift dependence is basically attributed to this parameter, where we have our usual dark energy density parameter. So both of them, the point we try to keep in mind at this moment is that both of them basically represent both phantom and non-phantom dark energy. Simply put, I am not talking about the details of scalar field description of dark energy. Simply put, phantom dark energy essentially means the equation of state is less than -1, whereas non-phantom means the equation of state is greater than -1. So that's it. And the third parametrization I will talk about is called generalized Chaplygin gas parametrization. Once again, this comes from quantum matter physics and all these things. Cosmologist has adapted this parametrization from them. This is once again a 6+2 parameter description. Instead of W naught and WA, here we have explained everything, the equation of state, in terms of A and alpha. But essentially, this is once again a 2 parameter description, and this is generalized so as to once again so as to fit the data in a better way than the standard Chaplygin gas. But one needs to keep in mind that unlike these two parametrizations, GCG basically represents non-phantom dark energy only. Once again, why I have talked about these three parametrizations, I will come in a minute. But along with that, there are several other parametrizations, and these parametrizations mostly have come of late. I will talk about these parametrizations later on after discussing the basics of dark energy from data. These parametrizations, there are several other parametrizations. Some of them are very, very popular, like Jasal, Bagla, Padmanabhan parametrization, W naught and WA. This is more or less similar to CPL, but this gives you a more stiff redshift dependence of WA. There are several other parametrizations as well. I will talk about them later on. Okay, let me try to come to the observation part in a bit details before trying to fit these parametrizations against data sets. As I talked about supernova type 1 data set, they are called standard candles. And here basically what we do is that we try to probe the luminosity distance via distance modulus, which looks like this. And essentially, as I already told you, in EN 2.1, there are several other data sets as well. That basically gives you a data set which looks like this. The red are the outliers, but the blue ones are the more important points for us. And these basically gives you, so what basically we try to do is that once we measure the luminosity distance from there, we try to find out, we try to fit one model against that data set, and we do the standard maximum likelihood analysis. How likely the model fits the data against this. This is a standard statistical measures. I'm pretty sure all of you know about this. So here the distance modulus that is coming from the observational data. Here I have my distance modulus from the particular parametrizations from the particular model I am considering, and this is the standard deviation. So we basically try to find out the chi-square and try to minimize the chi-square. Now, as it turns out, there are some nuisance parameter along with this. So we try to marginalize over the nuisance parameter using this. The data set that we use of late is that Union 2.1 compilation. This is 580 supernova. This has been used little bit earlier. Right now, and after that, this joint light curve analysis came, which is a combination of SDSS 2 plus SNLS. Right now, people mostly use Pantheon dataset, which is around 1000 data points. And also, there are some future datasets. Pantheon Plus is already there. This is around 1700 data points, but there is some confusion with Pantheon, so people prefer to use Pantheon. And then LSST is already running. LSST data will be coming very, very recently, I think, and DACE is already there. Regarding cosmic microwave background observation, as I already told you, our universe is black body. One can measure the temperature of the black body very, very precisely, and this background temperature turns out to be 2.725 Kelvin. But as I already told you, with the advent of experimental data sets, this COBE, WMAP, and Planck came. This is the map for Planck 2018. It basically tells you that along with the background temperature, there are very tiny temperature fluctuations in CMB, which is of the order of 200 microkelvin. From there, what we do is that we try to extract out the background and pick up the part fluctuations, and then try to take the 2-point correlation of the fluctuation. And that 2-point correlation function I have expressed, because CMB sky is spherical, I have explained everything, and people usually explain everything in terms of spherical harmonics. Those are the mathematical parts. I am trying to basically skip those parts. All we try to do is that along x-axis one can plot the CMB multipoles, and along y-axis one can plot the 2-point correlation function of the temperature fluctuations explained in terms of CMB multipoles. And this basically gives you a funny plot which looks like this. Okay. It's pretty surprising how the experimental data fits this funny plot very, very accurately. And from this plot, from the positions of the peaks as well as the heights of the peaks, one can find out uniquely the amount of baryonic matter, amount of dark matter, amount of dark energy, amount of temperature fluctuation, amount of very early perturbations of the universe, which is called power spectrum, its scale dependence, which is called spectral index, so on and so forth, also the optical depth. So these can be found out from here very, very accurately. Okay, please. Yeah, of course, of course, of course, of course. So in the context of dark energy, I'm trying to skip the other informations that are coming from CMB. In the context of dark energy, CMB gives you two basically important information. Number one is the shift parameter, that basically is a measure of the shift of the position of the peaks. So if you change the dark energy parameters, these peak positions will be shifted, and which may not be acceptable by the observational data. And there is something called integrated Sachs-Wolfe effect, which is actually given by the very low wells. So I'm trying to skip the ISW effect in this talk, and I'll mostly focus on the shift parameter. In the shift parameter, dark energy reflects on the position of the peaks through this parameter, which is called shift parameter, and this is actually measured by the angular diameter distance from today to the last scattering surface. And this shift parameter can be written like this, where this chi y is like whether our universe is flat, open or closed. This is an attribution to this, and y is the most important term. This basically gives you an integrated effect from today to the decoupling redshift, where the denominator basically takes into account all the cosmological parameters so far as the background is concerned. Where this, let me try to explain this. This is omega matter, which evolves with redshift as 1 plus z power 3. The curvature basically evolves as 1 plus z square. Omega x is attributed to the density of dark energy, and because we are yet to pinpoint to the equation of state of dark energy, this is kept as a free parameter Wx. So essentially we try to parameterize Wx in different manners, and we try to constrain these things using data once again. Using the same prescription, the chi-square analysis. So I'm not going to the numbers and all these things. This can be available in the literature. This is the latest data set, Planck 2018, although I have mostly put the data sets from Planck 15. Planck 18 is little bit improvement on that. Along with this Planck temperature anisotropy, Planck 18 basically replaces the low PW map by its own polarization data, but more or less essentially the numbers are of the same order. So these are the 6 parameter vanilla lambda CDM model, and the constraints from Planck 18 look like this. This is the baryonic matter, this is cold dark matter, this is the, as I said, the amplitude of power spectrum, this is spectral index, this is optical depth, and this is the Hubble parameter. So from Planck 18, the Hubble parameter, which is a measure of present acceleration of the universe, is obtained more or less like 67.31. I'll try to basically request you to keep this number in mind. I'll come to that point later on. Baryonic acoustic oscillation I have already explained. I'm not going into details of this thing because this is more or less complicated. So this is what we get from CMB, and this is what we get from large scale structure data, SDSS. From here, once again, we can estimate the angular diameter distance through this combination. dV is something we measure, which is a combination of angular diameter distance as well as the Hubble parameter. And till now, we have got 6 major data points from large scale structure data. 3 are coming at 3 different redshifts from Wiggle Z. 1 is coming from this one is coming from this one, and Boss data radius 2F gives you 3 data sets. Once again, we do the chi-square analysis for this. And the last one, as I already told you, this is the Hubble Space Telescope data, which is the one and only direct measurement of Hubble parameter. Once again, let me try to remind you, all the other experiments are the indirect measurements of Hubble parameter through the model. This is the one and only direct measurement of Hubble parameter. Old data set basically used galaxies as data points in the era of Hubble. Today, instead of using galaxies, we use type 1a supernovae in the Cepheid calibrations. So, as I have already told you, this is not, of course, this is not the latest data set. This is also the Union 2.1 data. No, sorry, this is not the Union 2.1. I'm sorry. This is the HST key project data set in 2001. But in the last 20 years, the data set has improved to a great extent. The data set, the most reliable data sets people use today are RIS 2011. Then Efstathiou came with a new kind of analysis, which is 2014. After that, RIS came with a series of upgraded data sets. All of them are 2016, 2018, 2020. I think 2022, there is another set of data release. But nowadays, instead of using RIS, people usually use this combination, RIS plus supernova, which is called SOOS data sets. Now, Why I took basically those 3 parameters. Dheeraj has already told you that we wrote we wrote a paper on this at the very early stage of Planck results. This is based on Planck 13, okay? And so this will basically give you the basic essence of fitting the parameters, fitting the cosmological models against data sets. So basically what we did is that we took these 3 parameterizations, CPL, SS and GCG. Let me once again try to remind you that these 2 are that basically can take into account both phantom and non-phantom equations of state, whereas GCG can only take into account non-phantom equation of state. Okay? And here is lambda CDM. So what we tried to do is that we collected all these data sets that were available around that time, just after the data release of Planck 2013, and then we tried to do the parameter estimation. The chi-square value, as we find out from here, is that this is the chi-square for lambda CDM. CPL shows slight improvement over lambda CDM, but this improvement is not statistically that significant for sure. And more or less GCG more or less is at par with lambda CDM, and SS is in between. So even though CPL shows little bit improvement of chi-square, and as we know, lower the value of chi-square, more favored the model is. So CPL is little bit favored than lambda CDM, but one should not take this difference too seriously in statistical language. Okay, these are all numerical values. Just to convince you that we have really worked hard on this. In fact, Dheeraj was a advanced PhD student around that time, and he did the, or beginning postdoc, yeah, beginning PhD student, beginning postdoc, and he actually did the most of the runs and all these things. So we basically tried to constrain all the parameters of these 3 parameterizations. The bottom line is this, that is summarized over here. I will try to argue, I'll basically argue to focus on the lower panel. So if we consider CPL, where both phantom and non-phantom are allowed, then we see there is a huge part where phantom equation of state is favored. So phantom is favored more or less at 2 sigma for CPL, more or less at 2 sigma for SS, but non-phantom is favored for GCG, and there is no surprise in that. Because for GCG, phantom was forbidden for the very beginning by the construction of the equation of state. This does not include phantom, but these 2, because they include both phantom and non-phantom, they basically tell you that there is a 2 sigma tension between early and late time experiments. Hence, there is 2 sigma tension with lambda CDM. So essentially, this, there's been couple of other papers as well which came almost at the same time. All of them pointed to the fact that lambda CDM, so far as the latest data sets are concerned, around that time, lambda CDM cannot explain all the observations very, very precisely. Though lambda CDM is the simplest model, but there is some level of tension with the data sets for lambda CDM. Yes, of course.
So what is the intention? Because taking into account all the datas.
Yes.
All
yes.
the data.
Right, right. I'll come to that point in a minute. So later on, I will try to do an analysis where basically I'll try to extract out direct measurement. So basically, I try to extract out direct measurement data from this thing. So this was a very early piece of work, where actually if you include that one, there also you find out direct measurement data vis-a-vis all the data taken together gives you a 2 sigma tension. But to be very honest, we should not include direct measurement data to this. So I'll come to that point later on. Okay. Sorry.
Table of chi-squared.
Yeah.
You had your chi-squared was around 10,000.
Uh,
How many, what is your degrees of freedom?
More than 10,000, yeah. Because CMB, you have a huge data set. Yeah. Okay. Fine. So it basically, so all these works taken together basically raises the question that whether we should really rely on 6 parameter lambda CDM, or you need to go beyond 6 parameter description and try to corroborate 6 plus n within quote unquote parameter description of the universe with data set. And also Planck 15 data came, which basically shows that Planck 15 basically, along with the data release, they basically said that there is a more or less 2.4 sigma tension with these data around that time. So this has been accepted by Planck 15 as well. And today this is a very well-known fact that along with this, there are several other data sets which are in tension with lambda CDM from moderate to high level. Like Panster's one data set that is in 2.4 sigma tension to Holikov 11, which is a length cohesive data set. If we combine that with R18, there is this 5.3 sigma tension. So essentially, lambda CDM is like 5 sigma is tension with present data sets. So all it tells you is that one needs to go beyond lambda CDM for sure. And this in general goes by the name of infamous Hubble tension. So just to summarize the old results, there are two different routes of measuring the Hubble parameter. One is the direct route, which is the late route, so to say, where all the other data sets are there. I just talked about 4 different data sets, but there are several other data sets which are taken together, and all of them more or less give you a value of the Hubble parameter, which is around 72, 73 plus minus errors. Whereas there is this early route of measurement of Hubble parameter, which we usually measure by fitting some model, and that basically more or less gives you a value of around 67 plus minus 2. So even though we have come a long way, Hubble measured a Hubble parameter which is 540 or 560. So we have come a long way. There is these measurements which gives you a value of the Hubble parameter at z equals 0 to z equals 1100. And we see that they are pretty close to each other, 67 to 73. It's not too high. But cosmologists are really greedy. And in the language of statistics, this is called 5 sigma tension. So we're really serious about that. Even though the values are too close, 5 sigma tension is something we need to take very, very seriously. Once again, this summarizes the values. The direct measurement basically gives you a value of, as I already told you, 73 plus minus something, and the early measurement basically, early universe measurement, but that basically gives you a value of this. Right, which one? This one?
The local measurements,
Yeah,
it's still 1.4.
1.4, yeah.
So it's, okay, 7, all right.
Uh,
It's 4 odd sigma.
Yeah, it depends. Yeah, the value 5 or 4, that depends on what kind of model you are using and all these things are there. So one should not take that number 5 too seriously, but it's like 2.5 to 5, so to say. Is that all right? Okay, fine. Okay. So we tried to find out what can be the possible reason in current observation. So we did a work back in 2019 with Ochita Bhattacharya, Ujjayini Alam, Kanhailal Pandey, and Subinoy Das. So this is a summary of this thing. This basically gives you the value of Hubble parameter from different observations. These are like WMAP9 gave you a value of this. Rees came, direct measurement, which gave you a value of this. After that, Planck 13, which give you a value even less than WMAP9. Efstathiou basically did a reanalysis of this and found out a value which is little bit higher than this. And then once again, Planck 15 gave a very low value, Rees 16 higher value, Rees 18 higher value, Rees 20 even higher value. So as it tells you, as time goes along, this tension between low redshift and high redshift values, high redshift data sets, that is basically goes on increasing and increasing. Which? Right.
20,
I
it
must
must
have-
be.
I must have made
some
some
different data sets.
Absolutely. I must have made some mistake over there. Okay, fine. Yeah, this is large error, but this should not be taken too seriously. So there is this Hubble tension, but as it turns out, this is not the only tension that is basically bothering the cosmologists. There are several other tensions. Out of them, one other tension is very, very important, which is called the sigma 8 tension. This is a measure of the density parameter at 8 H inverse mega per sec. This goes by the name of clustering tension as well. And once again, the value of sigma 8 can be measured from different observations, either directly sigma 8 or a value of which is called S8, which is a combination of sigma 8 and omega matter naught. And Planck basically gives you a relatively higher value, whereas clustering and Wick lensing and DACE, etc., all of them give you a relatively lower value. So once again, the early universe data that basically gives you a relatively higher value for sigma 8, whereas all the clustering data sets and Wigg-Lansing data sets that basically give you a relatively lower value of data set. So in this paper, what we tried to do is to try to find out if there are other tensions and anomalies like curvature tension, all the other things are there, but we tried to find out if there is a relation between these two tensions or they are separate. Okay. So what we did is that I am not going into details of this analysis is really involved. So all we did is that we considered a most generic scenario where we took two fluids, one is dark matter and dark energy. They may interact, they may not interact as well. The data will basically govern us. So they may interact and both of them may perturb. And then we wrote down the background and perturbation equation for this set. So we have dark matter and dark energy, they may interact. So in the background equations, background conservation equations, we have an interaction term. In the perturbation equation, we have an interaction term, and both of them are perturbing, so we end up at 2 background equations and 4 perturbation equations, 2 each density and velocity for dark matter and dark energy. That's the scenario. And then we have this generic parametrization, which is WDM effective, WDE effective. Effective essentially means we have attributed the interaction term to the equational state. Okay. So this is the effective parameter, this is the dark energy effective parameter, and we have kept open the C-square parameter as well, sound speed parameter as well. They are not taken constant, the data will basically govern that. No, we have kept them free as of now, but they are constant, they are not redshift evolving for sure. Thank you, they are not redshift evolving. Okay. So the advantage of considering this parametrization is that we have demonstrated that in our paper, that if you choose different values for these parameters, that basically end up at different kind of dark energy models. Like this is lambda CDM, this is non-phantom WCDM, phantom WCDM, modified gravity, one can have warm dark matter as well, and the most generic kill, one can have interacting dark matter and dark energy. And then what we do is that we take these all 4 data sets again together, we combine them and try to find out the combined chi-square, and we try to constrain these parameters from data. Once again, I am not going into details of all these things, this can be found out in the paper. The summary is here. The summary basically tells you, once again, is that if we consider dark energy to be phantom, then this is the Planck contour, this is Planck plus Riesz 16 contour, here also we taken into account Riesz 16. After, I will come to some papers where we basically didn't take into account. It is 16, and here we have taken into account Planck plus Bau plus JLA plus Riesz 16 taken together. So they are more or less consistent so far as phantom is concerned. But if we consider non-phantom, then there is Planck and these 2 data sets, they are basically apart from each other. So essentially all it tells us is that, first of all, once again, phantom is favored compared to non-phantom. Not only that, it gives you a very important information so far as the correlation between H0 and sigma 8 is concerned. It basically tells you both for phantom and non-phantom, there is a very strong positive correlation between H0 and sigma 8, which is more or less generic to present cosmological data. Why I say more or less generic? Because instead of considering CPL parametrizations over here, if you consider any other parametrization for dark energy, the results may be different. I'm deliberately telling you about this thing because one paper that we have already worked on that is going to come in the limelight very soon on this. Okay. Yes, please. Sorry? Systematics are more or less controlled. Like I mean, people have checked the systematics. For CMB, systematics have been taken into account very accurate. Systematics. I mean, she is talking about the combining data sets if systematics basically affect that. sorry. Across different data sets. No, actually, I mean, I understand your concern. So, right. So, all I can say is that each individual mission that basically deals with, that basically takes into consideration systematics, and that basically controls that. But I mean, combining these things is, and we also believe, please, sorry. And I think one thing I can tell you over here, in this exercise, what we did is that we tried to consider different possible combinations of the data sets. So first of all, we considered individual data sets, and then two data sets taken together, okay? Two of these two, like 1 and 2, 2 and 3, 3 and 4, then 1, 2, 3, then 1, 3, 4, like this, and then we combined. All of them more or less gave the same results. So that may be a partial answer to your question, but of course I appreciate that systematics is something one, yeah, of course. And also, I mean, please.
Different constraints correspond to on the left and the right?
Yeah. Okay. So I should have explained that. This is Planck
Okay.
plus direct measurement. And this is including everything.
Including?
Everything. Planck, direct measurement,
Okay.
all these things. So that's what I'm trying to point out. I mean, as you already pointed out, one should not club all of them together. Like, at least the direct measurement is something we should take into account separately.
So the Planck is lying underneath here, is it?
Yeah, right.
Okay, that's there.
Planck is, yeah.
So what's the lesson to be learned? That non-phantom, you don't have, I mean, I'm a little confused because I think in an earlier conclusion, you said that phantom is desirable.
Right. Same is true here.
Okay.
Because this is for phantom,
Right.
this is for non-phantom. Both of them show correlation between H naught and sigma 8.
Right.
Okay. But so far as so far as this plot is concerned, they are disjoint. So for non-phantom, they are completely disjoint. Whereas in phantom, Planck of course gives you a very, very large contour. But if you include RIS16 along with other data sets with Planck, then the contour size basically shrinks. But this falls within this thing. So they are consistent. For phantom, these data sets are consistent. Early and late time data sets are consistent. But for non-phantom, they are not consistent. They are disjoint. So this still favors phantom to some extent. But the additional finding over here is that both for phantom and non-phantom, there is this strong positive correlation between H naught and sigma 8. So if you try to increase H naught, sigma 8 should suffer, and vice versa. So you cannot essentially resolve both these tensions simultaneously.
But as you can move from left to right, there is a tilt. The correlation is changing.
Yeah, right. Because here I have considered two data sets only, Planck and direct measurement. Here I have considered all the data sets together. And that's what I am trying to point out, just to resonate with you, that direct measurement should not be clubbed. That is something I will show later on. Okay. So all we need to do is to consider indirect measurements together and try to find out the Hubble. If we really want to address Hubble tension, try to find out the Hubble parameter and compare that with the Hubble parameter measured directly. Because if we include direct measurement, then that will be highly biased towards direct measurement. Then this tension doesn't make sense to that extent. Okay. But till now we have included all of them and we have found out that there is a strong positive correlation between these two things, and because both of them are very, very important to us, we cannot just propose a very funny model and say that look, somehow I have alleviated the Hubble tension because I have done it at the cost of sigma tension. Okay. But as I said, this may not be generically true because so far as the dark energy parametrization is concerned, we have considered only the CPL parametrizations. We have considered the other scenarios as well, but for dark energy, we have considered only CPL. Okay, let's start. How much time do I have? I mean, I think I have already oversold.
Yes, so it is 4:30.
So maybe 3. Okay, so maybe in 5 minutes I should conclude. Okay, so let me try to go very briefly what we can learn from our future missions. There are lots of future missions that are coming. Some of them probe intermediate redshift, some of them probe higher redshift, so on and so forth. I will mostly focus on the gravitational resonance missions. These are some other future missions which are also coming. All of them will try to probe our universe directly or indirectly. Okay, so I will try to focus mostly on the gravitational waves missions. So in gravitational waves missions, that can give you the value of Hubble parameter in two different ways. If you consider low redshift measurements like in LIGO, that either can corroborate with SOOS results or that can talk about the systematics of SOOS. Okay? And if we talk about the intermediate redshifts like LISA or Einstein telescope or any other GW data sets, then it can give you a value of Hubble parameter, albeit indirectly, of course, through the models. This can tend towards the either of these true values, and then this can help us more or less give us a hint on which value to rely on, or it can give you a value which is somewhat in between these two values. And that will make your life even more interesting because that will lead to a tripartite tension. Okay, let me skip this part. So what we did in this series of papers, we have been doing these works right from 2020 till today, and some of the works are still going on. Let me try to be very brief over here. So what we tried to do is that we tried to take the mock data sets from ELISA and Einstein telescope, and then we employed 3 different statistical techniques. One is the Fisher matrix forecast method. The other one is the Markov chain Monte Carlo analysis. Using the mock data, we basically tried to constrain the parameters. And the third one is a completely non-parametric reconstruction of the Hubble parameter using Gaussian processes. It's a machine learning process. Let me try to skip all these parts. And then, as I said, there are other models as well. So on top of those, we have considered some other models. We have considered 6 models to be precise, which we thought of to be really interesting. One is of course lambda CDM, the other one is of course CPL. But along with that, we considered JBP model, Payday model, and then there are these funny VM and VM-Web models, which basically claim to have addressed Hubble tension to some extent. So first of all, we did a reanalysis of this because all these, I mean, they were not in the same platform. Some of them used old data sets, some of them clubbed all the data sets together, and so on and so forth. So what we tried to do is that we tried to take the latest CMB, BAU, supernova data sets, and RIS data set for sure, and tried to constrain the model parameters by clubbing 3 data sets together. Direct measurement data is something we keep apart, and then we tried to find out what is the amount of tension of the Hubble parameter from these 2 things. Let me skip a little bit because, yeah, so this is the result from forecast analysis for different values of the Hubble parameter. We tried to find out the amount of error from here. This is a little bit more interesting, which basically tells you, I'll give you a summary chart of this. So what we did is that we considered all these parameters, all these parameterizations models, and then we tried to constrain the model parameters using the mock data sets from ELISA. Okay? And these are the constraints as we found out. The constraints we tried to find out is, I mean, we tried to show over here is the Hubble parameter, equation of state parameter, and the typical parameters from those funny models, VM and VM-Web. Okay? And the third one is, as I said, using machine learning tools, we tried to reconstruct the Hubble parameter for different runs. So here is a summary. Forget about all these results. Here is a summary. So what we found out from here is that this is the amount of tension from current data sets for all these models. This is the amount of tension where these 2 models fare really well, but they are more or less engineered so as to fit that. The models are itself questionable, but we have to be very honest, we have taken those models into consideration. So these models should be taken more and more seriously. Now Fisher forecast basically gives you a value of this, value of the tension like this, sigma, I mean delta H naught. MCMC basically gives you a value of the tension like this, and Gaussian process basically gives you a value of this. So essentially the bottom line over here is that GW emissions have some prospects of relaxing the tension for a few parameterizations. The nature is not same, the nature is not uniform for all these parameterizations because each model does have its own essence. So, GW emissions have some prospects of relaxing the tension for a few parameterizations, but at least it does not worsen the others. But the tension is far from being resolved, as can be found out from here. None of them basically tells you that the tension is less than at 1 sigma, albeit these two, where once again these two should not be taken too seriously.
So, Pratik, one question, one comment here is that this is something that GW mission have some prospect of relaxing the tension. It all depends on what the GW mission is going to see as the mean value. If the mean value comes closer to the CMB, then we can say that it is going to be resolved. If it is in the middle between CMB and the REES, we can say that okay, it is trying to make them better. If it is if it is going on top of the REES, then we can say that it is making it worse, right? So on forecast side, can we really say that we have some prospect of relaxing the tension?
Absolutely. That's a very, very nice question. Let me try to explain my take on this. Okay. So, the issue is that what do we mean by tension? If there are two values like this, and if they have large error bars, then I can say that by increasing the error bars, I have somehow resolved tensions, but that basically doesn't solve my purpose. Okay. So, essentially we need to satisfy twofold challenges. Number one, we need to somehow see if the mean is shifted, and then if the error bars are also really, really small. Okay. Now, so far as Fisher forecast is concerned, I absolutely agree with you because Fisher forecast doesn't change the mean. It gives you some mean value and asks you to predict the error. Okay. But so far as MCMC is concerned, what we did is that we considered one's individual model, okay, and using its latest constraints, mean plus minus 1 sigma, we generated the mock catalog using the specifications of a particular GW mission. And then using the mock catalog, we treated it as real data and we tried to constrain the model parameters that helps us in changing the mean value as well.
That is true, but how many mock catalogs have you generated for MCMC?
I think for each model we have generated 500 mock catalogs and then taken an average of that, so that the results are not random. We tried to generate more mock catalogs and we tried to find out a time when this is more or less saturated. Absolutely, absolutely. I completely agree with that. So, all I want to say is that if we rely, because for mock catalog, whatever data is coming in future, that should be in collaboration with present data as well.
Yeah, in GW, okay. Let's say, I can even get 90 kilometer per second per megaparsec. It may be completely wrong as well, but I'm saying that these are three different statistical analysis based on this data which changes the mean, but it does not say anything about the it only we can say about the error bar on the future observation.
Definitely, I agree on that.
And depending on the mean that you are choosing, your fiducial model, you can say that whether you can get 10% improvement or 20% improvement on that particular thing.
No,
but improvement of the tension depends on what mean value that you are going to get in future.
Absolutely, absolutely. Yeah. So, we need to wait for the real data for sure, and that can be completely different from this. All I want to say is that, absolutely, I completely agree with it. All I want to say over here is that what we have done is we took the mean plus minus 1 sigma values which are consistent with present data set. And then we did this random sampling and generated the mock catalog. For Fisher, for sure, as I said, for Fisher there is no mean shift. For MCMC, it results in some mean shift which may not be the true mean shift when the real data arrives. That is something I agree with this. But so far as MCMC is concerned, okay, this essentially results in mean shift which is generated from the map.
Exactly. Yeah, that is correct statement. What I see as Fisher difference between Fisher and MCMC is that if what you are assuming in the Fisher is that these are multivariate Gaussian and there is no non-Gaussian nature.
Absolutely.
In MCMC, you are actually allowing non-Gaussian
absolutely.
skewness.
That's the best thing we can do in absence of real data.
Exactly.
But of course, definitely, I'm exactly on the same board. We need to rely on the real data. So, in absence of real data, that is the best thing we can do for sure. That's what I said. Yeah, exactly. Right. That's what I said. Right. That's what I said here. It can be close to Planck, it can be close to direct measurement, or it can be somewhere in between. So this is something we are going to rather, my intention is not to resolve Hubble tension. My intention is to check if at all future GW missions can help us. And if it helps, in which direction it can help. Okay. Of course, we need to wait for the real data for sure. So till now, what we found out is that it doesn't help in completely reducing the tension. It rather gives you a tripartite tension, so to say. If we rely on, once again, if we rely on this Mach catalog. But of course, we need to wait for real data for sure. I completely agree with you. Any other question? Oh, okay, fine. So these are just summary of rather fancy things of doing all these things. Then we worked with ET as well. We generated the Mach catalog with completely two different fiducials. I mean, just to answer to your question, one is using the late time fiducial, other one is using the early time fiducial. And we tried to see if they converge somewhere. Okay. Once again, we found out that for these fancy models, they converge, but which should not be taken too seriously. So far as these other more reliable models are concerned, they do not converge to that extent. So probably. Yes, of course, but I mean, it all. Yes, of course, I agree with you. But this, I mean, how the models are constructed, that is also a part of concern from theoretical point of view. Okay, that's why I've taken into consideration for that's my personal take on this thing, of course. Okay, fine. So this is just a summary. I'm not reading that out. I think all of you can do this thing. So basically, we urge the community to carry out forecasts using different methods so as to comparatively weigh and unweigh the pros and cons of each. If one really wants to do this business for future data sets, be it from GW, be it from supernova data, be it from other data sets, whatever is coming in the near future, so to say. So, thank you very much for your patience and for interesting questions.
Thank you, Supratikda, for this nice colloquium. And now the floor is open for questions. We already asked a few questions, but if there are questions from students and postdocs here. It is not audible from here.
What were those white contours in the CBM picture?
Which
There
one?
were some white, so in initial slides. So whenever
Here, before that, right?
yeah, just a normal picture of CBM
CBM.
fluctuations actually. So there was a white line there.
Which one? These
before
are
this.
data,
Yeah,
right?
this.
Before this?
No, this one. What are these lines?
Which ones?
These white lines.
Oh, this basically, this is called hemispherical asymmetry, which I didn't explain, okay? There are lots of other things involved with CMB data, which I didn't explain. I mostly focused on the dark energy part from here.
So naively, what it tells about the
I mean, if you can break it into two hemispheres, okay, then the temperature fluctuations above and below this hemisphere, they are not exactly identical. There is some level of asymmetry that is yet unexplained, so to say. Maybe if anyone else wants to add to that.
Thanks.
Or
There is a preferred direction, it says to
Preferred
a
direction,
certain extent that one part is more hotter than the other part. It's statistical anisotropic kind of thing. So it is still debatable. I think the present status is 3 sigma or something like that.
Right, absolutely.
But I think this picture is a little bit exaggerated regarding this red and this blue patch.
Right.
And to highlight this one.
Right.
Oh, online.
Oh.
Are there online questions?
Okay.
Shiva? There are no online questions. Okay. Sweet.
So I didn't quite understand what was being used from the LISA data. So you created a mock catalog of mergers, is it?
Right,
No.
right. Yes, of course. I'll elaborate on that. Maybe I can elaborate on that in my talk.
Sure, sure.
But let me try to, because you have asked this question. So, yes. So what we did is that, as I said, I considered one model. I took its mean plus minus 1 sigma from latest data sets, existing data sets. Okay? And then I considered the instrumental specifications for ELISA. Okay? And I considered different sources of error. One is the delancing error. I mean, there can be 4 different sources of error for GW emissions. One is the delancing error. The other one is the peculiar velocity error. The third one is the instrumental error. And the fourth one is the photometric error.
This is mergers of binaries.
Right, absolutely.
Okay.
And I considered 3 different generations. One is the POP3, other one is the delay, and the third one is no delay. POP3 is population 3 stirs, that is merger of binaries. No delay is like, it's assuming that whenever 2 galaxies basically merge, the black holes merge immediately, which is a very identical case. No delay is more or less a realistic case when basically one considers that there is some level of delay between these 2 phenomena. So accordingly, the number of events will vary, and the events will be rather the errors will come from there. Okay. So 3 different cases we have considered,
So
and I have plotted all this.
you needed only the errors. You needed only the
Only the
errors to.
errors.
Okay.
Right,
Okay.
absolutely. Once again, in absence of real data, I cannot say what is the mean value.
There is one question in Zoom.
Yes, please.
Srihari has asked, what is the difference between phantom and non-phantom here?
Here, as I said, I am not going into the.
Meant by phantom and non-phantom. Yeah. What is meant by phantom and non-phantom?
Okay. So simply put, phantom essentially gives you an equation of state which is less than -1, and non-phantom basically gives you an equation of state which can be greater than -1. Now, the field theoretical description of this is more or less complicated, because this comes from a Lagrangian. If you consider a scalar field, then the Lagrangian basically include the kinetic energy as well as potential energy. For phantom, the kinetic energy has to be negative. So from field theoretical description, it will lead to some level of instability, so on and so forth. But there can be other descriptions as well, because as I said, I am not motivating everything from the Lagrangian. I am trying to motivate from the equation of state perspective, and this equation of state can come from the modified gravity theory as well. I mean, there can be some modified gravity theory which can give you some level of equation of state, which results in an equation of state effectively that is less than -1 without including any phantom scalar field as such. So that's why I said I'm not trying to bypass the phantom scenario over here, but my job is to do something else. I'm not doing the scalar field description over here. All I'm trying to do is that if dark energy has an equation of state which can be both -1 and greater than -1 and plus minus and less than -1, then what can be the possible constraints on that from observation? So I think that is okay.
Any other questions? Okay, if not, let's thank Professor Pal again.
Thank you.